We are now at lecture 9.2. It's the second part of our discussion of heteroskedasticity. So grab your pens and your paper and let's get started. So this lecture is going to be on testing for heteroskedasticity. It feels a bit backwards because I've told you in the previous lecture what you do if you have heteroskedasticity in your model and without even knowing whether it's present. Now we're going to test for it. We're going to have three tests. I'm going to teach you three tests, three ways of testing. Might seem odd to have three tests for something because it's all the same thing. This is an example, though, where if you set up a null hypothesis that you don't have heteroskedasticity. And remember, that means that the variance of the error term is a constant. If that's true, then there's a bunch of things that follow from that. And the null hypothesis has a bunch of implications. So essentially, we're testing a few of those implications. So let's just jump right in. The first one is the Goldfeld Quant test. And here, the basic idea is you have the dependent variable, and then you've got a bunch of explanatory variables, and you're going to pick one of them. So you pick one of the x's that you think explains the heteroskedasticity. So that explains the change in the variance. Now, by that, what I mean is you think the variance of the error terms changes at least in one direction in your sample, and so you want to pick the x variable that looks like it's responsible. So let me give you an example. I'll just pull up some data here that I have. So this is from a study I did many years ago on water pollution rates around the world, kilograms per worker per day, graphed against income. So this is a sample of 128 countries around the world. And this is the income per capita in 1985 dollars, and then this is the water pollution rates, kilograms per worker per day. So classic heteroskedasticity. So you have at the low end here, all the data is clustered basically in a short range, 0 to about 0.006. But then you go up to 10,000, and now the range is twice as large. And so in this case, we would say as income goes up, the variance of the error term goes up. So the income variable explains the heteroskedasticity pattern. So we'll assume that we've picked one of the x's, and we'll call it z. So if it's x2, we'll say z equals x2. It just gives it another name. So the first step is rank the data by z. So when you get a spreadsheet full of data, it could be in any order, but what you're thinking of it so that it's ranked from low to high along the axis that we're interested in. Then omit the middle 20%. or some similar fraction. We'll go with 20%. That's the usual fraction. So then we call the number of observations dropped D. Okay, so in this case, I can't remember how many observations, but let's say it's 100 observations in this data set. So we take the first 40 and the last 40, and we drop out the middle 20. Then we run 2 regressions. One on the low sample, call that L, and one on the upper sample. I'll refer to that as U. And we compute the sum of the squared residuals for the lower sample and the sum of the squared residuals for the upper sample. And our test is that the sum of the squared residuals for the lower sample equals or doesn't equal the sum of the squared residuals for the upper sample. Okay, so remember the way we're thinking about these is, what if that's true? What if we have homoscedastic errors? So the variance doesn't change. If that's true, then these sum of squared residuals will be the same. So we take our regression, let's say we're regressing water pollution on income. Well, the sum of the squared residuals from the lower part of the sample will be the same as the sum of the squared residuals from the upper part of the sample. Now you can look at this and think, yeah, that's not likely to be true. That's the point of the test. Does that sum of the squared residuals change? And so our test statistic, we'll call it G. Well, we'll call it GQ, so we get Mr. Quant in as well. So it's the Goldfeld Quant statistic. It is the sum of the squared residuals for the upper sample divided by the sum of the squared residuals for the lower sample, as long as the top number is larger than the bottom number. If it turns out the data is convergent, so that the sum of the squared residuals from the upper sample is small compared to the sum of the squared residuals for the lower sample, just flip it over. What you want is that statistic to be greater than 1. So you calculate that statistic, and that number, G of Q, is distributed, follows an F distribution. And it has 2 degrees of freedom. So remember, the F distribution always has 2 degrees of freedom. And C and C. And C is 1/2 times N minus D minus 2K minus 2. So D, remember, is the number of observations we dropped out. K is the number of explanatory variables, the number of the x's, and so we calculate that, divide it by 2, or take half of that, and then we compare the Goldfeld Quant statistic to the critical values of the F distribution. If this test rejects, okay, so our null hypothesis, the null hypothesis is that there is no heteroskedasticity. So if we reject that, that means we have heteroskedasticity. Well then, in that case, you could then use Z as your weighting parameter for a GLS regression. Use Z as the GLS weight. So then you would run a regression that would be something like y over z equals alpha 1 over z plus beta 1 x1 over z plus, and so on and so forth. You could use that z parameter to choose your GLS technique if you're going to do GLS. However, when you do that, when you run the regression having divided everything through by z, you then retest the model. So then, like, you get error terms, which implicitly are divided by z. You'd use those and repeat the Goldfeld quant test. So you'd again omit the middle 20% of your data set, do the upper regression, the lower regression, and recalculate the test statistic. And hopefully that will have gotten rid of the heteroskedasticity. So you're going to do that because in R it's just a command. Like when you download the package to do this, it's just a command. You can do it, but it's actually not a very common approach to doing the test. So we will look instead at the Brush-Pagan test, which is more common. And here, suppose there are several z's. Okay, what I mean by that is, let's say you've got a large data set, which can often happen. So like you think about the data set used for assignment 3 with the wage information, and then you've got a whole bunch of variables. You've got education, experience, the education of the mother, education of the father. You've got the demographic variables. You've got lots of variables. Goldfeld quant can be a bit of a chore because you have to test all of them if you want to try to identify where the heteroskedasticity is coming from. All right, so with the Brush-Pagan test, you could just test them all at once. So maybe your model is that the variance of epsilon is equal to sigma squared times some function, and maybe it's a linear function of a bunch of the z coefficients. We'll say p of your variables. And it might also be the case that if you test just one of these at a time, you might not get the right information. You got to test them all jointly. So Brush-Pagan lets you do that, and it works like this. Run OLS and get our residuals. So by running OLS, what I mean is the underlying regression model. So you regress y on all the x's, and you get the residuals. And then we're going to compute the sum of the squared residuals divided by n. And now that's almost the estimate of the variance. It's the maximum likelihood version of the estimate of the variance. It's close enough. We'll call it sigma hat squared. For OLS, normally we would do n minus k on the bottom here. But this, it turns out, is an alternative version of it, and it's the maximum likelihood estimator. That part is not important for you to know. What is important is you run OLS on this. The individual squared residuals divided by sigma hat squared. And we're running that on this expression here. So it's gamma 0 plus gamma 1 Z1 plus gamma 2 Z2 plus gamma p zp plus an error term. We'll call it v in this case. So instead of using y as our dependent variable, we use the squared errors from the OLS regression, from the original OLS regression, but we divide everything through by this sigma hat squared, which is the sum of the squared errors divided by n. Then we form our test statistic, and the statistic is, we'll call it BP for the obvious reason. We'll call it BP, and it is the regression sum of squares divided by 2. So that's the regression sum of squares divided by 2. The regression sum of squares, in this case, if you have homoscedastic errors, then these are all approximately the same number, because this is an estimate of the variance of that one the one error term. So if you don't have heteroskedasticity, if all the variances are constant, then these numbers are all going to be roughly constant. And if you regress a constant on anything, you get regression sum of squares of 0. So in this case, the idea is the null hypothesis of homoscedastic errors tells us that the regression sum of squares of this model will be 0. So we're then going to check this against some distribution, because if we have heteroskedasticity, then this will be a large number. And in this case, the Brush-Pagan statistic follows chi-squared with p degrees of freedom under the null hypothesis. Why does it? Well, you don't have to know that. If you want to know it, you'd have to look it up in a more advanced textbook. But what this means is, if that's a large enough number that it exceeds the 5% critical value for the chi-squared distribution with p degrees of freedom, if that's a large number, then it means the null hypothesis is probably not true. So then we have heteroskedasticity. What do you do about it? Well, here the Brush-Pagan test doesn't actually give us the same kind of guidance as a Goldfeld quant test. Because, see, the nice thing about testing a general function like this is, if there is heteroskedasticity present in your data set, you can test everything at once, and it's there or it isn't. But if you find it, it's not clear with a function like that what you would do to construct a GLS model to fix it. You can still try, and as before, as I said previously, there might be an obvious candidate in your data set. It might be turn everything into per capita terms, or turn it into per dollar of GDP terms, or divide it through by something. That might get rid of it. And then once you do, when you do the transformation, retest it using the same test. So in this case, Brush-Pagan, see if the problem has gone away. The third test is White's test. Now, White is the same chap that we encountered last time, who came up with the heteroskedasticity consistent variance estimator. And he also proposed at the same time a test. It's like the Brush-Pagan test. You start by running your OLS regression. So you get your residuals. And then you run OLS on. So this time, instead of rescaling the residuals with their maximum likelihood variance, we just take the square of those residuals and we regress them on our Z variables. And this time we obtain the r squared from that. And the white statistic, W, equals n, the sample size, times r squared. And under the null hypothesis that there's no heteroskedasticity, that statistic W follows a chi-squared distribution with p degrees of freedom. So you would check how big W is against the chi-squared distribution. And so here the idea is, let's say these Z coefficients, they don't really drive heteroskedasticity. Let's say these are all the same. Again, you have a situation where you're essentially running a constant on a bunch of explanatory variables. You're going to get an r squared of 0 if you do that. So we're looking at how close the r squared is to 0. And similarly to Bush-Pagan, the advantage of this is you test all your possible explanatory variables for the heteroskedasticity at once. The downside is if you detect heteroskedasticity, it doesn't tell you which one of those you should use as the weighting variable to fix it. However, that's not a big deal. So our procedure is test for heteroskedasticity using Bush-Pagan or White's. Or you could use Goldfeld Quant, but it's more of a chore because you have to test all the variables one at a time. So it's fine to test Bush-Pagan or White's. And to be honest, there are some textbooks now that say if you're running a cross-sectional regression, just assume you have heteroskedasticity. Don't even bother testing for it because it's almost certainly there. So you test for heteroskedasticity, check for an obvious weighting scheme. Turn it into per capita, per dollar of GDP, whatever, if you can. Retest. And then if it's still present, use White's HCE. So this is how we deal with heteroskedasticity nowadays. There is a chance that using a weighting scheme will give you that generalized least squares solution that might fix it. If you retest it, maybe the problem's gone away, so that's fine. You can then just use OLS. But if it's still present, then you just use White's heteroskedasticity consistent standard errors. And let's see, I guess the final point is it might seem strange that you have, this is White's test statistic and it's chi-squared p, and the Bush-Pagan is chi-squared p, but they're totally different formulas. Why is that? These arise out of some asymptotic theory, which means that regardless of how the actual individual residuals are distributed, if you have a large enough sample, the transformation that we do here under the central limit theorem converges on the chi-squared distribution. And because it's dependent on your sample size and it's dependent on how quickly it converges to the target distribution, it can sometimes happen that you do the Bush-Pagan test and it says you don't have heteroskedasticity, and you do the White's test and it says you do have heteroskedasticity. Well, that's because depending on the sample, depending on the characteristics of the data, one of them might have converged more quickly than the other. So if you do both tests and one of them says you have heteroskedasticity, then assume that you do. And in your assignment, in your fourth assignment, you will go through the steps of running the test and then using R to generate White's robust standard errors, just so you see how the procedure works. I am going to leave it there. I know that's only 25 minutes in, which is a rather short lecture, and you might feel you're not getting your money's worth out of me this time, but we've actually covered everything I need you to know. There's more in the chapter, but it's a bit obsolete now, so no point dragging you through it. So that is it for heteroskedasticity. The next week, we're going to go through the same kind of thing, but we're going to talk about that autocorrelation assumption. What do you do if autocorrelation is present? How do you fix it? And how do you test for it? So, I'll see you next time.